Hello, this is your tutorial on how to complete the activity 3, Moving Stars and Their Planets. We've already begun this. You should have done 1 and 2, but I will go through those very quickly for those of you who have not yet done them. So part 1 of this activity has you examine gravity and orbits. And the concept is that for every action, there is an equal and opposite reaction. This is Isaac Newton's third law of motion. And it has you imagine that you have a ball attached to a string. Holding onto the string, you start to spin in a circle. So the ball orbits you like a planet orbiting a star. As you pull on the string, you feel the force of the ball pulling away from you. The ball feels a force pulling it toward your hand. The model shows how a planet affects the motion of a star. The directions say press the play button, so you should follow along as I go to start the model. You can change the planet diameter to explore the effect of larger planets on star motion. And you can change the planet type from a rocky to a gaseous planet to explore the effect of planet composition on star motion. So let's take a quick look at that. To manipulate this model, press play, and you can see the path of the planet going around the star. You can increase the speed or decrease the speed. You can change it to a gaseous planet, rocky planet, and you can use at the bottom to change the mass of the planet, all the way up to 50 times the mass of the Earth. The baseline position is 1 times Earth, so you're looking at a planet with the mass of the Earth and a star like our sun. Answer the questions. Question 1. The motion of a star caused by an orbiting planet is called a wobble. Why does the star wobble when it has an orbiting planet? Question 2. Based on your observations, what is the relationship between the movement of the star and the mass of the planet? So when stating a relationship, state how, if one of the things changes, increases, or decreases, what happens to the other. So with this one, you might state something like, as the mass of the planet increases, the movement of the star does what? And the movement they're referring to is the wobble. Does it increase, decrease, or does it have no effect? Question 3. What happens to the wobble motion of the star when the planet has a very low mass? And explain your answer. Question 5. How certain are you about your claim based on your explanation? And what influenced your certainty rating? So once again, when we write these, be sure that you use examples from the simulation. You should explain in your explanation that when you change the mass of the planet to a low mass, that whatever you saw as a result, did it continue to wobble or did it stop wobbling? Use that information in your explanation. I'll pause for a moment while we go on to part 2. Okay, for page 2, the Doppler effect. It says there are billions and billions of stars in the universe, and many of them have planets orbiting around them. This begs the question, if scientists are interested in finding planets, why don't they just look for planets? The problem with looking for planets is that planets are dark. This makes them very difficult to see in a dark sky, even with the newest telescopes. In contrast, stars give off light. This makes them visible in a dark sky. This is why scientists study the light coming from stars to look for planets rather than looking for planets directly. Recall that planets exert a gravitational force on their stars, causing the stars to wobble. Scientists can determine if a star is wobbling by looking at the light emitted by that star. Light can be thought of as a wave. Waves are distinguished by their wavelengths, the distance between peaks or troughs. The wavelength of red light is longer than the wavelength of blue light, as shown in the diagram. How does the movement of the star affect the wavelength observed by the telescope viewer? The model below will let you explore how the light from a star appears to change as the star moves closer and farther from the viewer. In this case, the viewer is on the other end of the telescope on the left side of the model. Press the play button to start the model. Use the slider to move the star toward and away from the telescope. What happens to the appearance of light as the star moves? Can you tell from the graph which way the star is moving? So to manipulate this model, press play. This wave is showing the light coming from this star and the telescope is on the left. The viewer is looking at the star through the telescope. Now you can change the star velocity using the slider below. You can have the star move toward the observer, or you can drag it and have it go away from the observer. Now you can look at the graph. I'm going to go ahead and pause this. You can look at the graph on the right and see how when we went toward the observer, the velocity went negative. And all that means is it's going to the left on the view screen here. It's going toward the observer. And then we had it move away from the observer and went to the positive. When I brought it back to center is where it was going straight. We can clear the graph and take a look at the questions. The first one has you take a snapshot. Add notes that show which wavelengths are short and which wavelengths are long. It says take a snapshot that shows both short and long wavelengths. So in order to do that, you'll have to press play, make short wavelengths by having it go toward, and make long wavelengths and having it go away. Then you'll have to catch it a little bit faster than I did. We'll try that again. Play, short wavelengths, long wavelengths. I'm actually going to do short wavelengths at the end and then pause. Now that allowed me to freeze it where there's both short and long wavelengths. Now I can go to my question 7 and take a snapshot. This will open up the other screen with a snapshot, and it's going to have you label. Add notes which show which wavelengths are short and which wavelengths are long. So simply you can use the arrows or the lines or draw on it however you want to show using a color that we can see where the long and short wavelengths are occurring. Okay, I'm going to go ahead and close this. Now that is saving my image. It should save your image as well. Mine isn't labeled, so I would need to go edit that if I needed to add my labeling. Question 8. You observe a star through a telescope. What happens to the apparent wavelength of the star's light as it moves toward you? Does the wavelength get shorter, longer, or would it stay the same? And explain your answer. Okay, I'll give you just a moment. We're going to move on to part 3. Okay, part 3. If you've already done parts 1 and 2 earlier, now is the time to focus on part 3. How is the star moving? It says a scientist observes that the light from a star seems to be yellow in the visible portion of the spectrum. Okay. It says, based on the observations, can the scientist be certain that the star is not moving? Yes or no, and explain your answer. How certain are you about your claim based on your explanation, and explain what influenced your certainty rating? So you're just answering the question that a scientist observed that the light from a star seems to be yellow in the visible portion of the spectrum. Okay. And then, can the scientist be certain that the star is not moving? So you're making a claim here. So base it on evidence. Your evidence can come from this model. So if you take a look at the models, can you change anything to, to keep the light yellow, moving toward or away? I'll give you a moment to work on this, and we'll go to part 4. In part 4 of this, we're going to learn about the importance of the angle at which we view the planet orbiting the star. It says, in the Planet Hunters video, you learned that there are 2 ways scientists use a star's light to look for planets: the wobble method, Doppler technique, and the light intensity or transit method. You have used models that show how a planet can cause a star to wobble, and learned how movement can affect a star's apparent wavelength. In the model below, you will explore how the angle of a planet's orbit or tilt around a star can influence a scientist's ability to find that planet. You have seen that a planet moving around a star moves the star, but scientists don't have an overhead view like you've seen in the model. They use telescopes to see stars. In this model, the telescope is at a right angle, 90 degrees to the screen. Imagine that you're looking through a telescope at the screen. With the right orbital tilt of the planet, you will be able to see the star's motion on the velocity graph as the star moves toward and away from the telescope. Your challenge is to find an angle of orbit that maximizes the motion of the star toward or away from you, and an angle of orbit that prevents you from seeing any motion of the star. So press the play button. Let's see if I can get that back to normal. Okay, I'm going to press the play button. Now you can tilt this by, I'm clicking on my touchpad and dragging it so I can change the angle. So here we're at a 90-degree angle. We're looking straight from above onto the star and planet. You'll notice in the graph, there's no way we can tell the velocity of the star relative to you. The planet's going around the star this way, so the star is not moving toward nor away from you. But you can tilt it. And as we tilt it, we can see now we're sensing some amount of wobble. Okay, we're seeing where the velocity of the star is moving away from us and then toward us. There is a key up here to show. Moving away is in the positive, moving toward is in the negative. And you can see we kind of replicate that right here. Question 14. Which orbital angle or tilt prevents you from seeing the motion of a star that does have an orbiting planet? So would that be 0, 45, or 90 degrees? So what you should do is go back to it and check. The tilt degree is in the lower right. So 90 degrees is here. 45 degrees is about there. And 0 degrees is straight on. So if you don't know, you can always manipulate the model in order to find out. Okay? Explain your answer. So when you explain your answer, you should indicate that when you adjusted the angle of the graph, describe what you observed. How certain are you, and what influenced your certainty rating? and you're answering the question, which orbital angle, 0, 45, or 90 degrees, prevents you from seeing the motion of a star that has an orbiting planet? Okay, I'll give you a moment and we'll go on to the next one. Part 5. Absence of wavelength shifts. A scientist looks for planets by studying the light from a newly discovered star. The velocity graph of the star's motion, based on shifting wavelengths, indicates no motion of the star toward or away from Earth. The scientist decides the star doesn't have any planets. Do you agree with the scientist? Explain your answer. How certain are you about your claim based on your explanation, and what influenced your certainty rating? When you're explaining what influenced you, remember to always think of, what don't you know? Is there something that you might not be aware of? Understand that with these models, we don't have all the information. We'll go on to number 6. I'll take a moment for you to catch up. Part 6 is called The Importance of Mass. The mass of a planet plays a crucial role in how much a star will move. The angle at which the planet orbits its star affects our abilities to detect it. The combination of planetary mass and orbital angle affects the shape of the velocity graph created by the shifting wavelengths of light. In the next model, you'll change the planet's mass and orbital angle to see how different combinations of mass and angle can result in similar velocity graphs. The model is set up with a medium-sized planet orbiting the star. The velocity graph of the star is shown here. Be sure to note the scale on the y-axis. This motion caused by this planet is very, very small. You can use the zoom button on the graph to see small movements of the star. Your challenge is to set up the model with a very large, very heavy planet that results in a similar velocity graph to the one you see up here. So we're trying to replicate that. So let's look at the graph. It goes from 0 to minus 0.2 to plus 0.2 meters. And it's very small amount. So I don't know how much it's moving. If that's 0.2, then 0.1 meters would be about here, 0.05. So maybe 0.03, 0.025. It's very small. So we have to try to replicate that with a very large, very heavy planet. So let's do that first. If I press play, I can see my velocity graph here. And remember, if I click on the touchpad and move it, I can change the tilt. So I can certainly change the motion of the graph. Now, are you noticing anything with the graph? The x-axis, let's talk about the y-axis. The y-axis isn't labeled the same. So I'm going to go ahead and click zoom once. Well, that really brings it together, doesn't it? I'm going to clear the graph. And if I click zoom, I'm going to go even here, play around with this a little bit. You can see I'm struggling myself. So if I click zoom, it's changing the y-axis because it's really not moving much. So I'm going to have to try to move this, but I'm also going to create a very heavy planet. How heavy? I don't know. What's very heavy? Let's go halfway. Can I make a graph that looks like the one at the top of this page, which is this graph here? So this is too big, all right? The graph I'm seeing goes from minus zero point 0.2 to zero point 0.2 meters. I've got a larger planet than Earth, so what do I have to do? I have to decrease the angle. I'm going to go ahead and clear the graph so I can start off even again. I'm going to decrease the angle some more, clear the graph, and just play around with this a little bit. It looks like we're getting pretty close. I think it's still too much because the one I have here is from 1 to minus 1, and the one we're trying to match is from minus 0.2 to 0.2. Well, we're pretty little of a change here. I'm going to go ahead and click zoom to see what happens. It's still too much. See if I can decrease the amount of tilt. I don't want it all the way gone. Clear graph. Let's see what happens. I'll click zoom. Yeah, it's still, well, that's pretty close. That looks pretty good. If you look at the parameters, that's not bad. It doesn't look the same, but we're going to let it run a little bit, see if it kind of reconciles the y-axis a little bit. But I'd be fine with that if you want to use that one, something like that. But you play around with it. I'm not going to worry too much. It says, take a snapshot that shows a very large, heavy planet that shows the velocity of the star between negative 0.2 and 0.2. Mine does that. Maybe not enough. So I could do a little more of it. Clear graph, see what happens here. See how close we are. And zoom in. Still too much. It has to be between those two numbers. Oh, I'm sorry. No, I'm wrong. 0.2 and negative 0.2. So we can go a little bit more of a... All right, you go ahead and do your best. I'm wasting too much time of yours right now. I'll probably fast forward through that part. So explain how different combinations of planetary mass and orbital angle can create similar velocity graphs, right? So if you increase the mass and decrease the angle or whatever, how you can end up with the same. And the point of this is the difficulty that an astronomer might have to determine how big a planet is. This velocity graph was recorded by pointing a telescope at a nearby star. A scientist determines that the star must have a very large planet orbiting around it. Okay, so velocity graph, here it is. Doesn't seem to be moving a whole lot. Do you agree with the scientist's conclusion? Explain your answer. How certain are you? And what influenced your certainty rating? Do you think this graph, do you think the scientist is correct in determining that the star has a very large planet orbiting around it? Note the scale of the graph. It's different than the one we used. I'm going to go into the next one. I'll give you a moment to catch up. Now we get into some noisy data here. What does that mean? In previous models, the telescopes you used displayed perfect data, generating very smooth velocity graphs of a star's motion. In reality, scientists have to use instruments that are less than perfect. Interference from our atmosphere, as well as space, dust, and gases, also blurs the telescope's vision. The data scientists collect has lots of noise, fluctuations in the data to both natural interference, atmosphere and dust, and the limits of the tools. So, check it out. Both these graphs show the same orbiting planet. Why do they look different? This would be a perfect telescope on the left. This is more realistic. Noise caused by the physical environment and limitations. Early telescopes could only detect a star's wobble if the movements were larger than 7 meters per second. Newer telescopes can detect wobbles as small as, let's call it less than 1 meter per second. The detection ability is improved because the data from the newer telescopes are less noisy. New space-based telescopes will be even better at spotting smaller changes in velocity because they do not have to see through Earth's atmosphere. Does this graph show a planet orbiting a star? Can you see anywhere where the planet might be moving the star back and forth? So you select no, it's just noise. Yes, there's definitely a planet, or I'm not sure if there's a planet. The change in velocity is small. What more information would you want to be sure? Would you want to be sure of your answer? And something that's always good for this would be more data, just a longer sample size, if that makes sense, to see if you can see a repeating pattern. Let's go to number 8. We're almost done. This one is called Finding Planets Through the Noise, Angle. The next model produces more realistic telescope data with noise. You will adjust the precision of the telescope using a slider. In reality, the only way to get a higher precision is with a breakthrough in engineering or scientific knowledge. Explore the effect of orbital angle with noise. So you're going to, number 1, position the orbital angle tilt of the planet so it is close to, but not exactly, 90 degrees. So I'm going to go ahead and do that. Close to, but not exactly 90 degrees. We'll say 87.2. That's close to, but not exactly. Well, okay, 86.65. You go ahead and set yours however you want. Make a planet that you can just detect on the velocity graph without using the zoom button. The telescope precision, then set the telescope precision to perfect. So first, let's do this. We're going to go ahead and press play. All right, can you detect a planet? I can change it, right? I can change the diameter of the planet. I can increase it until I start to see movement. I'm looking at my graph. Oh, I think I see an up and down movement. Barely see an up and down movement here. It's above the line, it's dipping below the line. So I was able to do that. Now, the telescope precision is already perfect. So it says to set it to that. So that's 100%. Then it says, change the precision of the telescope to explore how varying the level of noise affects your ability to detect a planet. Change the orbital angle to see how the combination of orbital angle and telescope precision affects scientists' ability to find planets. So I think you'd agree that with a perfect telescope, we can see where that there's a planet orbiting the star. But now let's decrease the precision. Let's go down to about 50%. I can't really see it very well, but I'm going to increase the speed to see if that helps me with the graph. Why don't I just go ahead and clear the graph? Clearing the graph gives us a fresh set of eyes to it. And telescope precision. Let's go to 50% again. I'm going to slow this down. You can see the noise start to come through. And how that affects your ability to see if it's moving toward or away. Now it's set to do some experimenting. Let's take a look at the questions. Most of the planets that have been discovered orbit their stars at a tilt closer to 0 degrees than to 90 degrees. Why is this true? And why might a scientist using modern telescopes be unsure about having discovered a planet? So hopefully there you're taking a look at the angle the planet might be and so on. We can move it like this, and you can see even with big planet diameter but horrible precision of a telescope, right? You can still see the movement of the star, the wobble of the star caused by the planet. I'm going to move on to the next one. I think you guys should be caught up pretty well. The last page, finding planets through the noise. We're going to take a look at mass. Okay, this says explore the effect of planetary mass with noise. Set the telescope precision glider to its perfect setting of 100. Now mine was there before and it is there now. At the very bottom you can see. You should do this on yours. Make a planet with a small mass and select an orbital angle that allows you to detect the planet. Then change the precision of the telescope to explore how varying levels of noise affects your ability to detect the planet. Okay, so I want a planet with a small mass. Well, let's do Earth size. Play. Looking at the graph, I'm going to change the angle. Well, we know what the best angle would be, right? That would be 0 degrees. Can I see the wobble here with 0 degrees? I'm not seeing any wobble, so I'm going to change the planet diameter. I'll drag it up. I'm starting to see some motion there. Oh, that's a pretty good wobble right there. I'm looking at the graph. Now I'm going to change the precision to see what effect that has. Drop it down. And I've always said, go to the extreme to kind of get the relationship. And we can go all the way down to 0, but I'll do that, or to 5%. I'll do that slowly. Okay. And there's 5%. And let's say this wasn't directly head on. Let's change the angle a little bit and see what happens. As we let this run, as we finish up, let me go ahead and go to the questions. Most of the planets found have been very massive. Why do you think that is? And hopefully you're understanding the relationship between the idea that small planets don't move their stars as much as massive planets. Question 33. This velocity graph was recorded by pointing a telescope at a nearby star. Based on the graph, could there be a planet orbiting this star? Explain your answer, and you're done. So that was a fairly long activity. Hopefully yours does say congratulations, and those points will be recorded in HASBOT here, and I'll check those as well. So make sure you get those done today, and tomorrow we will continue learning about exoplanets. Let me know if you have any questions.